on the von Neumann algebra M, I look at the set of cocycles Z with respect to the action sigma phi, the modular action, of R and M. These are the sigma phi cocycles. And an element in here is a map from R T to W of T in M, which is SO continuous. Such that instead of Vt plus S is equal to Vt Vs, you have to have Vt plus S. It's equal to Vt sigma T phi of Vs on one side. And because we do not assume that Vt are unitaries, we will see, we will put also this condition, namely that W of T, of minus T, it's equal to sigma T minus 1 of V of T star. If you assume that they are unitaries, this condition is automatic. And okay. Now, the point is that this is fixed. Then there exists psi, a normal semi-finite weight on M, such that d psi divided d phi, the conical cycle, is equal Vt. That is the theorem I want to prove first.
W2T could be identically 0, right?
Sorry?
W2T can be identically 0 and still satisfy that equation.
Yes, and then you have the zero weight. And then you have the zero weight.
Only normal semi-finite.
Yeah, so normal, yeah, it's normal semi-finite, you know. Okay. Then you have the zero weight, and that's perfect. Okay. So let's construct this weight phi. The construction is in several steps. First, we take F infinity, it's equal B of L2 of R. And I denote here by Eij, Ej from 1 to infinity, a set of matrix units. And because I put this notation here, I will denote by En the sum over k from 1 to n of Ekk. And we will denote by phi, I will consider M tensor F infinity. That means the matrices, infinite matrices over M. And for an X in here, which has the matrix Xij, if you prefer, I write it as sigma Xij tensor Eij. We denote by capital phi, phi of x, it's equal to the sum from k is equal to 1, from k is equal to 1 up to infinity of phi of x k k. This is for x in here, which is positive. This makes sense. Well, then this is again an NSF weight. And we are interested what is sigma t phi of x, in general x. It will be sigma t phi of x tensor the identity. Now, how to see this equality here? Take this projection En and look at the algebra En M tensor F infinity En. And look at the restriction of capital Phi to this algebra. The restriction is the following. It is sum from k to equal to 1 to n, right? Okay, but this is what? This is exactly the balanced weight. You put phi, right, on the diagonal. And we saw that then the sigma t phi restricted to En M tensor infinity of En will be equal to this sigma t phi of x11 sigma t phi of x nn. And this means exactly, in the tensor language, means exactly this thing. So this is valid on this algebra, and now En, this En, converges to the identity. So that this accounts for the proof that indeed we have the another thing, another kind of an argument we can give is the following. This phi here is nothing that phi tensor the trace, exactly. And then sigma t phi is equal to sigma t little phi times sigma t trace. Well, this is not a simpler proof than the one I gave, because this notion here is not very simple. In general, if you put two NSF weights. And this was the first step. Now, we do the following thing. We take, again, the translations. Ut of psi of r is equal to psi of r plus t for psi belonging, sorry?
I assume this is that there is no, finally this does work, there is such a, this big phi is also an NSF weight.
Yes, of course.
And then each modular group will be the tensor product of the modular groups.
Yes, it is in general for two weights, phi 1 and phi 2. You have to define carefully what is phi 1 tensor phi 2, and then you have to prove, and I am proud I proved that. Dickerness assumed it, and I proved that the modular group is tensor product. But this is not a trivial matter. Okay, so I take this for psi in L2 of H of R. Okay, and I write ut, I take the analytic generator of ut, a to power it, and a new weight, phi prime, which is phi sub 1 tensor A. The Peterson-Takesaki construction with this analytic generator. What follows then? It follows that sigma t phi prime it's equal to add 1 tensor ut times sigma t phi, and that means this is sigma t phi tensor add ut. So we have constructed first the weight capital phi, then capital phi prime. Now we define another weight making use of the cocycle. The cocycle here is a map from R to M. Every function defines a multiplication operator, so that I will first make this identification H tensor L2 of R. It's, if you take a psi tensor F, a function in here, you associate it to the function T goes to F of T psi, which belongs to L2 of R with values in H. And this is an identification, if I put here the whole cross tensor product. And then what you have, you take from H tensor, you take the operator W of zeta in T, for zeta a value in here. W of zeta is equal to simply Wt times zeta of T. And this defines an operator W. W commutes with M prime tensor C. That's obvious. And this is M tensor B of F infinity, the commutant. So that this operator V commutes with the commutant, so this operator is in M tensor F infinity, where the weight phi prime, capital Phi prime, is defined. And W, because of the conditions put there, W is a partial isometry. And if you assume the cocycle is unitary, this will be a unitary operator. Okay, now, what I want still to do is to define psi, a new weight, which is phi prime of W star W. And I want to know what is sigma t of this new weight. So this is, you remember very early I defined for phi a state and V a state phi sub V. This is the set, and there we computed the modular automorphism group. The modular automorphism group makes to intertwine the following operator, W times sigma t phi prime of W star. Now, this is defined by T is going to V of S, by S is going to V of S. The function is the multiplication by this function. Now, what is this thing here? It's easy to see. It's the multiplication by the function S is going to sigma t phi of W of S minus T star. And if you multiply these two functions, this function times this function, it's equal to the function S going to W of T. Is a constant. Is a constant function. So that we get that sigma T psi is equal to add of Vt, this Vt in here, composition with sigma T phi, and tensor add ut. So the translations were put into the game in order to get this thing here. You see the translations appearing here. But now we want to get rid of the translations. And to get rid of the translations, we apply again the Petersen-Takesaki theorem to find another weight psi prime such that the modular automorphism group will be add V of t sigma t phi tensor the identity in here. It's clear. I will take the generator, the inverse generator of the translations, a to power minus 1, and put in there. So that we got this. We got this fourth weight with this automorphism group. Okay. Now we take P in M tensor F infinity, any minimal projection, I'm sorry, P in F infinity, any minimal projection. And I look at a projection 1 tensor P. 1 tensor P, M tensor F infinity, 1 tensor P is the same thing as M, the initial algebra. If you like to see, this is X, and it's going here in X tensor P. This is the map that makes the identification. Okay. Now, we define as psi prime an NSF weight, normal semi-finite weight on M in the following manner. M, which is equal to 1 tensor P, M tensor in F infinity, 1 tensor P. Namely, we put the following thing. Psi prime is equal to capital Psi prime restricted to 1 tensor P, which is because of this form of the modular group, 1 tensor P is in the centralizer of Psi prime. And this one defines a weight on this algebra and hence on this algebra. So that is Psi prime of this one. And you came back. We already defined the restriction of a weight to a projection in the centralizer. And this is the sense in here. What you get then is sigma t psi prime, the small psi, is equal of x, is equal to sigma t of capital Psi prime of x tensor P it's equal to, look in here, it's Wt sigma t phi of x, right? Wt star tensor p, which is identical with only this thing in here, right? Okay. Now I have to define the weight itself. So I will consider, I will put here, this is sigma t, sigma t psi prime. It's equal to add of v of t composition with sigma t of phi. Okay. And now what I do, I take w prime of t, which is d psi prime d phi t. Okay. And then what you have? You have on one side that this is equal to this one, and on the other side it's equal to, because of this thing, is add of v prime t composition with sigma t phi. So these two things are equal, which means in particular that we have this AT. I put W prime T star WT. This is in the center of M. It's in the center of M because of this equality in here. Okay, and well, for what I'm writing here, it's better to assume from the beginning that the cocycle is unitary. If not, it's something which happens on a reduced algebra. So this is an a to power it. It is a generator. It has a generator in here. And because of the two cocycle identities, this is indeed a unitary group. Because both of them are cocycles. And the bad part of the cocycle property is cancelled by this equality in here. So the last thing we do psi, it's equal to psi prime, the small psi prime, times this A. And that's it. Because then d psi d phi t, it's equal to d psi, this is d psi prime A d psi prime times d t times d psi prime divided by d phi t. And d psi prime d phi t, this is w prime of t. And what you get here, you get, maybe I put a minus 1 here in order to have a minus 1. I get vt, v prime t star. And this cancelled, and I have vt. So that, indeed, every cocycle corresponds to a normal semi-finite weight once you fixed one weight. This theorem of Alain Kohn is a strong argument for considering weights Not because weights do not exist on an algebra that is not countably decomposable, but the fact that the variety of cocycles corresponds with a variety of all weights, infinite also. And this is indeed a very strong argument for considering weights. Okay, that's it. I finish it.
Is there any condition when that will be a state?
Sorry?
Given a cocycle, is there any condition that it will correspond to a state?
No, I don't know this thing. I don't know. I don't think there is a condition that shows that a cocycle corresponds to a state.
I would like to make a comment here. Here you have the appearance of regular representation of real lines, because I are called the translation. And this, and then here we see the sigma sub t clause are the UT popping up is being used. This is in the cohomology theory. This is called Shapiro machinery. Namely, what in mind, around the mind, what happened is if you tensor with the regular representation, any cocycle become co-boundary.
Yeah.
And if co-boundary, then unitary translation.
So this is kind of co-boundary.
Yeah. Yeah. Okay. So this is the Shapiro machinery. At the same time, for the unitary group representation people, this is the following fact. Any unitary representation, tensor with regular representation, could create a multiple for regular representation. Which is also very known fact. Yeah. So that's what is being used.
Well, if you don't look so generally, you look just at the proof, the role of the regular representation was to compute correctly this cocycle and to find that he is a constant function.
When I communicated with Alan about the duality theorem, and I immediately decided that with the duality theorem we can prove that there is some way the cocycle. Using duality machinery.
Okay, I will go now back to the standard form of an algebra having a bicyclic vector in order to go a little bit further in the structure of the standard form. And namely, what I will do, I will consider, so M in B of H with psi naught in H bicyclic. Okay. Now, for every psi in H, we already considered an operator which I will call now, it was called capital X at that time. An operator L psi, I put 0 with the domain of L psi 0. It's equal to M prime psi 0, and such that L0 psi of X prime psi 0 is X prime psi. And what we know that this operator L psi 0 is affiliated to M. And moreover, L0 psi of psi naught, it's equal psi. Okay. Now, this operator, L0 psi, is closable. We have seen it. It's closable if psi belongs to the domain of F star. It was at that time. But now we know that F star is S. It's closable if it is symmetric. Is that okay? Fine. Okay. Now, I want to see when L0 psi is a positive operator. Unbounded, of course. It's positive if and only if for all x prime belonging to m prime, L0 psi of x prime psi 0, that means x prime psi, times x prime psi 0, is bigger than 0. And that means that the form omega, the vector form omega psi 0 of x prime star x prime is positive. That means that this vector form omega psi naught is a positive form. And so that L psi 0 is positive if and only if omega psi 0 prime, because I consider this vector form on the commutant, it's bigger than 0. Okay. Good. I will denote by L psi the closure of L psi 0. Okay. But on the other hand, you can consider the closure, but on the other hand, because L psi 0 is positive, it has a self-adjoint positive extension, namely the Friedrichs extension. So that it has a Friedrichs extension which is a positive self-adjoint A, which is still affiliated to M, as was the operator L0 psi. Okay. Then what we have, this A will stand for the Friedrichs extension of this operator, and we have that psi 0 belongs to the domain of A, and A of psi 0, it's equal to psi. Sorry? A of psi 0 is equal to psi, and so L A psi 0, it's contained in A. This is for all computations. Now, what we will consider will be a cone. A cone, I will baptize it P sub S. Is on the side of M, not on the side of M prime. P sub S are all the vectors psi in H, such that L psi 0 is positive. That means this is the set of all psi belonging to H, such that the form omega prime psi naught is a positive form. Or this is the set of all vectors of the form A psi 0, where A is affiliated to M and is a positive self-adjoint operator. Okay. Now, it's clear that this is a cone, convex cone. We will come back to the study of this cone and of the analogous cone associated to a star, that means on the side of M prime, later. For the moment, we concentrate on this cone, and what I will show is the following lemma. That for every normal positive form phi on M, there is a unique vector psi in this cone P sub S, such that phi is equal to the vector form omega sub psi. In particular, it follows that there is a self-adjoint operator positive affiliated to M, self-adjoint positive, such that the vector psi naught belongs to A, domain of A, and the phi is equal to omega A psi naught. I will consider first the uniqueness. So let's consider two, psi 1, psi 2 in PS, such that the vector forms omega psi 1 and omega psi 2 are equal. Then it follows that I have the norm of x psi 1 square is equal to the norm of x psi 2 square, so that, and this happens for every x belonging to M, so that there exists a partial isometry such that I have V prime such that I have the following thing: V prime of x psi 1 is equal x psi 2, and V prime restricted to M psi 1 orthogonal is equal to 0. Now, with this definition, because of this equality, it follows that V prime belongs to M prime. It commutes with every x in the algebra, every operator in the algebra. Well, in particular, we have the following thing: V prime xi1 is equal to xi2, V prime star xi2 is equal to xi1, and hence what we have is the fact that omega prime psi 2 psi 0 is equal to omega prime V prime psi 1 psi 0, is equal to translation to the right by v prime of omega prime psi 1 psi 0. Well, instead of writing so, I could put here v prime to the right, I'm sorry, dot v prime. Okay, but I leave it so. On the other hand, what I have here is omega prime psi 1 psi 0. It's equal to omega prime v prime star of psi 2 psi 0. It's equal to translation to the right by v prime star of omega, okay, of omega psi 2 psi 0. Now, this and this are positive. Prime also here are positive because Xi1 and Xi2 are in PS. Okay. And now by the uniqueness of the polar decomposition, now what is this? This is a normal linear functional, which is written as a partial isometry times a positive form. And the partial isometry has the first, the initial projection equal to the support of this. Then this is a polar decomposition, and the polar decomposition for forms is unique, so that what we get omega prime psi 1 psi 0, it's equal to omega prime psi 2 psi 0. So notice that this proof of the uniqueness has some very non-trivial element, namely the polar decomposition thing. Okay, and now we have m prime psi 0 is dense in H, so that this means that psi 1 is equal to psi 2. Because you apply it to an x prime, the x prime will go to psi 0, and these are dense in H, so that Xi1 and Xi2 are equal. So this was for the uniqueness. Now for the existence, I have to quote one of the form, namely the third form, I think, of the spatial theorem of von Neumann. Namely, by von Neumann, I had this normal positive form given on M. M has a separating vector. It has a bicyclic vector. But because it has a separating vector, every normal positive form is a vector form. So that by von Neumann, there is a vector zeta in H such that phi is equal omega zeta. Okay. Now consider the polar decomposition of omega prime zeta xi 0. It's equal to the polar decomposition. This is a partial isometry. I mean the commutant we did. Psi prime. Good. This is the polar decomposition. Fine. And we define then psi is v prime star of zeta. And then what we have? We have the following thing. We have omega prime psi 0 is equal to omega prime v star here, v star zeta, zeta xi 0, And it's equal to, that means the translation by, this is a V prime here, the translation by V prime star to the okay. It is omega zeta xi0. Okay, and this is, if you look in here, it's exactly psi prime. So this is positive. So that this form is positive. That means that psi belongs to PS. And then what we see is omega prime zeta psi 0. It's equal to R V prime of psi prime. That's the polar decomposition as there. It's equal to R V prime, omega prime. This one is equal to psi prime. So I replace this by this. Omega prime psi naught, which is omega prime V prime psi naught. The two things are equal, so that it follows that zeta is V prime of xi. And then for every x in M, we will have the following. Phi of x is equal to omega zeta of x. It's equal to x zeta xi. I'm sorry, x zeta zeta. Is equal to x zeta times zeta was V prime of xi. This is V prime star x zeta times xi. I went with the V prime star. Is in this. This is equal to, you have a commutation here, x V prime star of zeta xi. And this is equal to x xi, because xi was V prime star of zeta, x xi xi. Good. It's omega xi of x. And that's the proof of the lemma. I am going now to a theorem proved by Professor Takesaki in his lecture notes even. But first of all, I will introduce some simpler definitions. So I take a positive self-adjoint operator in H, and by En I denote the projection, spectral projection 0n of A. And that's for every n in N. Okay, I will say that A is of summable square, so that this is the notion that is defined. Square with respect to phi, if you have the following thing, the sup of phi of a square an, the sup over n is less than infinity. And then I will denote this sup by c. It's a finite positive number. Okay. Then it follows that phi of a square en, it's of course increasing, and increases to c. Good. Now, I take an x in M, and M bigger than n, natural numbers. And I look at phi of A EM, x A EM, minus phi A En, x A En. I will see that this is equal to, well, you do the usual things. You put a mixed term in here, and you will get two differences. And after that, you apply to these two differences, you apply the Cauchy-Schwarz inequality. And applying the Cauchy-Schwarz inequality, you get finally that this is less than 2 mod norms of x, c to power 1/2, phi of a square En minus phi Em here minus phi of a square An in here. So this converges to 0, so that also this converges to 0, so that this is a Cauchy sequence, and then the limit exists. The limit when n tends to infinity of phi A En x A En, this exists and deserves a name, which I will put it so, LA RA of phi of x. Well, something like phi of AXA is this thing here. Okay. So that, let me consider a particular case. If phi is a vector form omega xi, then A is square integrable, square summable with respect to this phi, if and only if xi belongs to the domain of A. This is just a definition of the, even by functional calculus. That okay. And in this case, what you have that LA RA of phi is equal omega A xi. In the case, consider it here. Now, with this preparation, I can state a theorem which is due to Takesaki, even in lecture notes was proved. So very early was proved this theorem. So you have phi and psi normal positive forms on M. M is in B of H. Okay. And the assumption is the support of phi is less than the support of psi. And then there exists a positive self-adjoint operator affiliated to M, positive self-adjoint, such that the support of A is less than the support of psi, the big one, and the small one, phi, is LA RA of psi. Moreover, if S of psi, the support of psi, is finite, then A is uniquely determined. Now, a small comment about this theorem. This is very much a Radon-Nikodym theorem, because in the usual Radon-Nikodym theorem, you assume that a measure is absolutely continuous with respect to another measure. And here, you assume exactly this thing, that the support of phi is less than the support of psi. And then this, or maybe A square, is a kind of Radon-Nikodym derivative. Okay, let's go to the proof. Of course, we may assume that the support of psi is equal to 1 because everything happens under the support of psi. Okay. And we use the GNS construction so that we get an isomorphism P M to N, a von Neumann algebra, which is N, is P psi. P is P psi of A, which is included in B of, let me put K, because H is already busy. Okay. Such that you have P of 1 is equal to 1, is a unit almorphism, and you have a bicyclic vector, let's put it psi sub naught in K, such that you have that psi is equal to this vector form, omega psi naught, composition with P psi. Now, then you can transfer phi from here to here. And you get, so that from M you transport phi of phi, and you get another form. I will call it theta on pi psi of A. And so that phi will be theta composition with P, with theta one normal positive form of this algebra and uniquely determined by that. Okay. Now, I apply the lemma I already proved, and it follows that this form, theta, it's a vector form, omega of B psi naught, with B affiliated to N, positive self-adjoint. But now theta and this B is in here. I can transport by isomorphism B to here, back to M. And then I say that I see that we have the following thing. If I put E, so B is transported to A, affiliated to M, positive self-adjoint. And I denote by En is the characteristic function 0n of A, and Fn the characteristic function 0n of B. And then we have psi of A square En is equal psi of, I'm going slowly here, P minus 1 B square Fn. Okay, this is omega zeta 0, well, I put here zeta, xi 0, omega xi 0 of B square Fn. This is then the norm of Fn B xi 0, the square of the norm of this thing, because of course Fn commutes with B, and B square Fn is Bfn square. And this is less than B psi naught square. So that indeed A is square integrable, so I will put something like this. It's square integrable with respect to psi. Okay. And finally, what we have that LA RA of psi in X, it's equal to the limit when n tends to infinity. This is the definition of psi of A En X A En. Now this is equal to psi of, this is P minus 1 of Bfn X P minus 1 of Bfn, which is the limit when, the limit here when n is going to infinity, which is the limit when n is going to infinity of omega xi 0 of B En pi of x Ben. This is then omega B xi 0 of P of x, which is theta of P of x, which is finally phi of x. And that ends the proof. Now, concerning the uniqueness, in the notes you will have some more details. An operator affiliated to a finite von Neumann algebra has a normal operator affiliated to a finite von Neumann algebra has a unique extension to, LC0 has a unique extension at a self-adjoint operator. This is because of the finiteness of the algebra, and this gives the uniqueness of the operator A. The details are in the, the details are in the paper, but for the result I quoted, I sent to the lectures on von Neumann algebras. It's a simple result. Okay. Let's go a little bit further for the last part of my talks in here, but it will last the last 3 days also. I go just as far as I can now. So that the uniqueness in the finite case here is not a difficult result. I think that from this theorem of Takesaki will follow the theorem of Sakai. If phi is less than psi, then the operator you get there can be an operator between 0 and 1. And this follows also by detailing a little bit the arguments in here. So that with some work, a corollary is the theorem of Sakai. If phi is less than psi, then phi is equal psi a point A, when A is positive and less than 1. And this should follow from the theorem announced before. Okay. So we preserve the notations we introduced here, namely the domain of the operator L0 xi is equal m prime xi 0, and L0 xi of x prime xi 0 is equal x xi. And the operator, as I said, L0c, it's closable. Sorry? Thank you. The operator is closable in the following two cases: if either xi belongs to the domain of S, or the case we used, if L0 xi is symmetric. If it's symmetric, it's included in an adjoint, and that's the reason it's closable. Okay. We denote then, in this case, L xi is equal the closure of L0 xi. Okay. We introduced a cone PS, which was equal to xi in H, such that L xi is positive. And this was the same thing as the xi in H, such that omega prime of xi 0 is positive. And is the same thing as the vectors of the form A xi naught in H, where A is affiliated to M, positive, self-adjoint. And xi naught belongs to the domain of A. Well, similarly, we define an operator R0 eta, with the domain of R0 eta, it's equal to M psi 0, and R0 eta of psi 0, it's of x psi 0, x psi 0, it's equal x eta. And you have the same commentaries like here. Good. So that we get another cone, PS star. PS star, which is the eta in H, such that R eta is positive. This is all the vectors eta in H, such that omega on M of eta psi 0 is bigger than 0. And is the same thing as the set of the vectors of the form B psi 0, where B is affiliated to M prime, positive, self-adjoint. And psi 0 belongs to the domain of B. These two are convex cones. And as we will see immediately in the proposition that will follow, it follows that these convex cones are polar to each other. More precisely, we have the following lemma, proposition even, proposition. Well, I will state the proposition, and I will not do the details, because the details are extremely simple, but they take time, they take some space, say. So I will, for the proof, I will send to lectures for Neumann algebras, page 260. And namely the following. You take a vector xi in H, and then R equivalent the following. First, xi belongs to PS. Second, xi belongs to the domain of S. S of xi is equal to xi, and L xi is positive. 3 is that xi belongs to M plus applied to psi 0 closure in the Hilbert space. And fourth thing is that psi eta is bigger than 0 for every eta in PS star. Okay. Similarly, R equivalent for eta in H, R equivalent J is eta belongs to PS star, double J. Eta belongs to the domain of S star. S star of eta is equal to eta, and R eta is positive. The 3 J's is that eta belongs to M prime psi 0 closure, and the fourth thing, GW, sorry? I'm sorry. Yeah. Psi 0, like here, of course. And it's that psi eta is bigger than 0 for every psi in PS. So I repeat, the proof of this proposition is almost trivial but tedious for writing. Among other things, you will get some kind of polarization relation somewhere, which is trivial, but you have to write a lot with them. On the other thing, another thing which is easy to see is the fact that the domain of S is equal to the linear envelope of PS. The domain of S star is equal to the linear envelope of PS star. I put the same thing, page 262. This. Now, one more thing is that with the same kind of approximations as we did for the Tomita algebra, we will get the following thing, that for any psi belonging to a second, that means m psi 0, there is a sequence psi n in the Tomita algebra such that the first thing is that psi n converges to psi. S of psi n converges to S psi. 2. L psi n converges strongly operator to L psi. And I will put SO star. That means also the adjoints of these operators converge strongly. And the third thing is that L psi n is less than in norm than L psi. That's just what we did when we saw that the Tomita algebra is very rich, and the same kind of arguments. Now, from this proposition, if you look here and here, you get the following thing, that J PS is equal PS star. And because you have S psi is equal psi for every psi in PS, you can put here JS, and if you put JS, you recall that S is J delta power 1/2, so that J square is 1. So what you get the delta power 1/2 of PS is equal PS star. And that means that delta power 1/4 of PS is equal delta power minus 1/4 of PS star. And because of this, we will consider another cone which is neutral with respect to S and S star, or M to M prime, which is equal to the closure of this and the closure of this. And what we will see that this is a self-polar convex cone. And I will go further with this self-polar convex cone. If you look at standard von Neumann algebra and you put into the picture also S, G, and also J and P, then you will get what is called a hyperstandard von Neumann algebra. And there are many properties specific to the hyperstandard algebras. In particular, we will see that there is a canonical implementation of forms with vectors in P, and on the other hand, that any star isomorphism between two hyperstandard algebras, that means exchanges the J's and the P's, is uniquely implemented by a unitary operator. Up to now, we know that it is implemented by a unitary element, but if you ask the unitary element to preserve J and this P, then that unitary will be unique. This means a very important thing, namely that the automorphisms of M correspond to unitary elements in the hyperstandard form. And then, because we've been speaking about the topologies on the automorphism, the uniform convergence of the pre-dual of the automorphism will be exactly the same thing as the strong operator continuity of the corresponding unitary implementing the automorphism. So that we can call this topology on the automorphism the natural topology on the automorphisms of M. Thank you very much.
Yeah. What is standard form or hyperstandard form?
Now, I didn't define what is hyperstandard. I said that just the following thing, that if you take into account J and P, then, and you put some properties in there, then that will be a hyperstandard form. So the hyperstandard form means to consider the von Neumann algebra together with J and P. And we will have a formal definition.
There are some modular there may not have.
No, well, if you would like me to go a little bit further, a hyperstandard for Neumann algebra is a von Neumann algebra such that there exists a conjugation in the Hilbert space and a self-polar cone P such that this, and this. These are satisfied by J in here and the P in here. But you would say that you can say it abstractly with some J and some P. And what is important is that if you have a von Neumann algebra with a bicyclic vector, and you have this von Neumann algebra hyperstandard, that means having its own J and its own P, then its own J corresponds to this natural J in here, and the P corresponds exactly with this cone. But it's quite a long way up to that. We have still 3 days. And these 3 days, we will be swimming in this area. Okay. So I will give you the whole papers up to the end to be put on the site. But please give them me back in order to have also tomorrow a cheat sheet, right? And be careful when you scan them, because I noticed some other inversions. Page 70 is before page 69 or so. But it doesn't matter because there are the... So, what is... Well, I will take care of them.